Hello everyone, my name is Jingwei. I am talking about the joint work with Feng, Yang, Wenyuan, and Guanci. The topic is about privacy-preserving naive-Bayes classifier using homomorphic encryption. As we all know, machine learning has been involved in various fields recent years. Data owner can use machine learning techniques to training a model from massive amounts of data. Once we have the model, we can supply services to, for example, we can classify client's data that to be classified. However, a security incident continues to occur. The demand for privacy-preserving machine learning is rapidly increasing. For example, the model may be sensitive, such as a financial model, disease diagnosis model. Also, clients' data may be sensitive, such as credit history, medical records, and so on. To solve this contradiction, here we consider a framework of privacy-preserving classifier. In this framework, the model is already known, so we don't consider how to learn the model from the data. To simplify the framework, we consider the model provider is also the service provider, so the computation will be executed by the model provider. This makes our framework is a two-parties computation. And the clients, in this framework, clients sample data and the results will be encrypted. And the red box is called the classification phase. In this framework, we consider the threat model is honest but curious. It means the adversaries execute the framework, but he can learn as much information as possible. In the literature, there are many related works, such as Post, etc., Li and Kim and Yasumura and Sun. All the previous works consider how to classify clients' data by using naive-Bayes classifiers based on homomorphic encryptions. There is a common feature of the above methods. That is, during the classification phase, interactions are needed, which increases the communication burden, also increases the possibility of information leakage. Our main contribution is propose a privacy-preserving naive Bayes protocol. which is non-interactive. That means during the classification phase, it is the red box. In the red box, there is no interactions between the client and the server. We use homomorphic encryption scheme BGV to encrypt the client's data. It is thought to be post-quantum safe. The main technique we use is an algorithm to compute the argmax function of an encrypted array. Let's begin with some backgrounds. First, we recall Liu-based classifier. Consider a dataset with S categories, and each sample has n features. Each feature can take at most t different values. Then, to classify a sample data X, we need to compute S star. Essentially, it is argmax function of an array. The elements of the array consist of many operations among many probabilities. They are prior probability and likelihood. As we know, probabilities can be very small. To avoid the underflow, we can just take logarithm and get the new formula. Actually, it is better than the previous one because it converts multiplications to additions. Okay, here is a definition of homomorphic encryption. We consider the public key case. Homomorphic encryption scheme first is a public key encryption scheme. And there is an evaluation algorithm to evaluate the functions, such that the decryption of the evaluation is just the evaluation of that function on the plain text data. If the function f has an a priori bound on the depth of its circuit, it is called leveled FHE. If the function f is an arbitrary computable function, then it is fully homomorphic encryption, which depends on a technique called bootstrapping. The bootstrapping step is very expensive. In this paper, we use BGV scheme, which is one of the most efficient leveled HE homomorphic encryption scheme. And the plain text space is this polynomial ring decided by parameter m and p. And we can pack many data in one plain text because the plain text space is isomorphic to a vector space over some finite fields. This technique sometimes called SIMD and sometimes called batching. The ciphertext space is this polynomial ring HLEAP is an implementation of the Guizhou crypto system, and it supports the SIMD operations. It also supports some basic homomorphic encryption operations that we will use as basic tools. Now we introduce some building blocks. The first one is algorithm for computing the multiplication between a plain text matrix and an encrypted vector. Here we just use some technique like Z is unencrypted. We encrypt each element of the vector Zi as an ciphertext and just do something like plain text multiplication of a matrix and a vector. This algorithm only needs plain text ciphertext multiplications and ciphertext additions, so it costs no ciphertext multiplications. The next one is comparison among encrypted integers, which is a recent work due to Ilyashenko and Luca. Essentially, this method is to compute a listen function over encrypted data. The listen function is defined as follows: if x is smaller than y, then the function equals to 1, otherwise equals to 0. The method essentially is to interpolate it by the following polynomial over Fp. This is a polynomial with degree p minus 1. So we can evaluate this polynomial within at most this number of ciphertext multiplication dips. Based on the comparison, we can construct our main building block, the argmax function of an encrypted array. Indeed, given an array, the argmax function of this array can be expressed by this expression, which depends on the less than function defined previously. So, to evaluate this function, we need t times t minus 1 over 2 comparisons and cost at most log 2 t plus the depths of the less than function totally. So combine the basic tools and the building blocks, we can construct our protocol for privacy preserving naive-Bayes classifier. The input of the client is the sample data, the key pairs, secret key and public key. The input of the server is the information about the model, that is likelihood information and the prior information. Actually, we can observe that the classification phase, it is step 3 to step 6. In the classification phase, low interaction between the client and the server happens. So this is the non-interactive protocol. The security comes from the security of the FHE scheme we used. So if we assume a secure homomorphic encryption scheme, the protocol is also secure. We give a rigorous proof in our paper. Now we present some experimental results. We use UCI machine learning repository. We use two datasets. The first one is called Iris. In this dataset, there are 3 categories, and each sample has 4 features. Each feature has at most 5 values. We use 8% of the samples to train the model, and the others are used to test. We use this set of parameters for the homomorphic encryption, and the security parameter is about 100. According to our test, for predicting 3 test samples, it costs 5.42 seconds. On average, it costs about 0.18 seconds for each sample. As we indicated previously, when for this parameter set, we can pack about 2,000 data in one ciphertext, in one plaintext, also ciphertext. So we can compute about 2,000 samples at the same time. So amortized cost is only about 2.7 milliseconds, and the accuracy is about 97%, which is almost the same as the plain text space. Another dataset is Wisconsin breast cancer. For this dataset, we have a better performance because in this dataset it supports about 4,000 slots in each ciphertext. The accuracy is also almost the same as the plain text data. Now let's conclusion. We proposed a privacy-preserving IO-based classifier based on the Jingwei homomorphic encryption scheme, which is secure against the quantum attackers. In the future, we can do some work on more efficient classifiers and more classifiers in this framework. And the full version of this paper can be downloaded from this address. Okay, that's all. Thank you.